In this video, I'll be doing the complete breakdown of all major subfields in robotics and artificial intelligence. I'll be taking up a case study to talk about the major subfields in one particular problem, that of pick and place using a robotic manipulator system. And at the end, I'll also give you a framework that would help you to choose a subfield for yourself. So I'll start first by talking about the major subdomains in robotics. Then I'll go on to artificial intelligence and talk about the subfields in AI. And then I'll take the case study and connect all of the subfields of robotics and AI, or most of the fields of AI, and show you how these actually work in a typical robotic system. And at the end, I'll be showing you how you can choose a subfield for yourself. So we know that robotics is very interdisciplinary. It is at the intersection of mechanical engineering, computer science, and electronics engineering. So let's take all of these fields one by one. So when it comes to mechanical engineering, there are four major subfields in context of robotics, and that would be, of course, mechanical design, kinematics and dynamics, modeling and simulation, and manufacturing. For electronics, also, I have classified the major fields of electronics as applied to robotics into four major categories, and that is controller design, sensors and actuators, communication, and power electronics. For computer science and artificial intelligence is a subfield of computer science. I have categorized it into software engineering, artificial intelligence, networking, and data science. Now it gets complicated in the sense that there are fields at the intersection of mechanical engineering and electronics engineering. There are fields at the intersection of electronics and computer science, and also at the intersection of computer science and mechanical engineering. So we'll talk about each of these intersections one by one. So first, what are the fields that are at the intersection of mechanical engineering and electronics? It's a field called mechatronics. And another important aspect or a field that is common to both mechanical engineering and electronics engineering is control systems, which is an essential part of robotics, which is absolutely critical for robotic systems. When it comes to the fields at the intersection of computer science and mechanical engineering, I've classified it into three categories: computer aided design, computer aided engineering, and computer aided manufacturing. For the fields at the intersection of computer science and electronics, Internet of Things, cyber physical systems, and embedded systems are the three major subcategories. So overall, as you can see, robotics consists of a lot of different fields. And in order to actually work as a roboticist, you need to have some level of understanding of at least a few of the major domains in robotics, have a broad understanding of some of the major domains, and also have an expertise in one specific subdomain. And I'd be talking about how you can choose your subdomain or your niche in the vast domain of robotics at the end of this video. So now let's move on to talking about artificial intelligence. So artificial intelligence has majorly five categories, and that is machine learning, natural language processing, perception, knowledge representation and reasoning, planning and decision making. So of course, a few of these fields also have intersections within themselves. For example, machine learning has intersections within computer vision, which is part of perception. Computer vision consists of conventional computer vision, which is mostly image processing based, and non-machine learning applications for image tasks. Another category would be machine learning applied to image tasks, and that implies that there are intersections within these fields. Likewise for natural language processing, but majorly there are these five categories. So let's talk about each of these categories one by one. So machine learning primarily has three categories: supervised learning, unsupervised learning, and reinforcement learning. When you deal with labeled data, when you have images, for example, and they are labeled, for example, instant images of cats and dogs, and you know which image has a cat in it and which image has a dog in it, you have the labeled data, then you use an approach called supervised learning. When there's no such labels available, then you use an approach called unsupervised learning. Another approach which is particularly interesting for systems where immediate feedback plays a major role, for example in robotics, is reinforcement learning, where an agent or an algorithm would actually take an action, change the state of the environment, receive some feedback in the form of a reward, and the cycle continues and optimizes itself to perform a certain goal. So this is reinforcement learning. And then the most popular buzzword in machine learning and AI is that of deep learning, and deep learning is nothing but a special case of machine learning when we use a larger network. And the primary difference between machine learning and deep learning is that the feature extraction process that is done manually in machine learning is done automatically. The feature is done automatically in a deep neural network, in a deep learning approach. And this is done by capturing the essence of the features in the weights of the neural network. So don't worry if you're not familiar with machine learning or neural networks. I just want to give a overall picture, give you the overall picture, and tell you about all the major subcategories of robotics and AI. And I'll be talking about a case study at the after I've classified all the subcategories of robotics and AI, and that would give you a practical sense of how most of these categories are actually used in a real world robotic system. And another particular subcategory of machine learning is evolutionary computation, which uses evolutionary strategies such as CMAES and other similar algorithms. And it is arguable that among researchers and academics whether or not evolutionary computation is part of machine learning or not. Some of the researchers believe that it is part of machine learning while others do not. However, in this particular case, I have classified it under machine learning. Then moving on to natural language processing, it can be classified into three major problems, three major categories: syntax, semantics, and pragmatics. Moving on to perception. Perception consists of three modes of perceiving the environment, and that would be vision, recognizing the speech, and haptics when it comes to using tactile sensors. For knowledge representation, I'm just naming the specific subcategories of it: ontologies, logical representation, and uncertainty reasoning. So knowledge representation essentially points to the category where you need to represent data in a structured way that can be then used in a particular stage of the robotic system pipeline. And you could research on each of these categories individually. It would take a lot of time explaining each of these categories in detail. And the goal of this video is essentially to just outline all the major subcategories for you so that you can explore each of the fields independently or in an interdisciplinary project and get an overview, get a really good background on a majority of the fields on robotics and AI. Now, talking about planning and decision making, classical planning, heuristic search planning, and rule based representations are the major categories. And these include popular approaches like breadth first search, depth first search, and also Dijkstra's algorithm, A-star algorithms, all these kinds of things. So you could easily look up each of these individual subcategories and start learning more about these. Now, as you can see, these are a lot of subfields. Alone in robotics, we see so many different categories. And also, if we take up artificial intelligence separately, we see that there's a lot of subcategories, and depending on different applications in robotics and so on. And so you do not really need to learn all of these subfields of robotics and AI. What you need to know is a broad level of understanding of at least 5 to 6 fields, and then eventually have a sub field of your interest where you want to achieve mastery in. So that is the main idea behind this. And to connect all of these buzzwords, these fields that I have mentioned so far, to an actual problem, to an actual robotic system, I've taken up a case study, a simplistic case study, where I'll be talking about a pick and place application using a robotic manipulator system. And this involves design, development, and implementation of the overall system from scratch. And how is such a system developed from absolutely nothing at all. And that is why it would include mechanical engineering, electronics engineering, computer science, and also artificial intelligence to perform this particular task. And hopefully, the main idea is that I want to give you a practical understanding of how each of these fields play a role. So let's start with mechanical engineering. So as we know, for a robotic system such as a robotic arm, a robotic manipulator arm of 6 degrees of freedom, of 6 joints, we basically need to manufacture a lot of different individual components. And for that, we would first need to design each of these components so that the robotic manipulator arm is able to perform tasks in a factory setting, in a household setting, in a research setting, or whichever scenario the robotic system is meant to work on. So for mechanical design, you would of course need to design each of the arm links. You would have to make sure that all of the arm links are necessary enough to perform the overall task. For example, the reachability of the overall robotic manipulator system should be enough such that it is able to reach the objects that it is intended to reach. Joint motors, end effector, the gripping system has to be designed, and mechanism design would be a major category of this. Assembly of all the major components, the wrist, the base, and all of the individual joints. So all of these would need to be designed individually. Mechanical engineering concepts, the design concepts would need to be utilized to actually build the overall system. And these would include also performing stress analysis, making sure that all the components have the right dimensions, geometrical considerations are taken into account, and all these things. So these would fall into mechanical design. And then moving on to modeling and simulation. So we don't just want to don't just want to design a robotic system, we also want to test the robotic system in a simulated environment so that the cost of actually performing experiments in a real world, which is very high, is avoided. And that can be done by making a virtual robot model in a simulation setting, and also an environment model using a simulation engine or a physics engine, and having a sufficient level of rendering, and also analysis and validation of the simulation and modeling system. So this is one particular category. And then the most important category, especially for a robotic manipulator system, is that of kinematics and dynamics. And kinematics and dynamics deal with homogeneous transformations, defining the transformation frames of each of the joints, the end effector, the base, the world reference frame, such that we can then define the movements of each of the individual joints with respect to each other, and also with respect to one universal reference frame. And then comes the concept of forward kinematics and inverse kinematics. Forward kinematics is simply put, when you know the joint angles, when you know the individual joint angles of a particular robotic arm, and you want to find the location, the position, the orientation, the acceleration, the velocity of the end effector. You do that by something called forward kinematics, which is basically nothing but simple mathematical geometrical calculations that involve the use of matrices and linear algebra and stuff like that. And then another thing would be inverse kinematics, which is the opposite of forward kinematics, as the name says. Inverse kinematics deals with finding the joint angles of the robotic manipulator arm given the end effector positions. So this is the opposite scenario. And then of course, for a particular problem, a trajectory or a path of a particular robotic system, robotic arm need to be defined, and that is done also using kinematics and dynamics by a concept called trajectory planning. And then of course, not just kinematics, dynamics, the impact of forces and torques have a is of profound importance in a robotic systems, whether it be a legged robot system, whether it be mobile robot, whether it be a robotic manipulator arm, as in it is in this case. So kinematics and dynamics, the primary field of robotics, mechanical engineering. And then designing is not just enough. The whole purpose of designing is so that the robotic system can then be built in the real world, and the way the system is made is by using manufacturing technology. Each of the individual components need to be manufactured, whether it be processes like 3D printing, which are increasingly being used in a lot of different fields now, whether it be welding, whether it be using casting to manufacture some of the components, or whether it be any other manufacturing approach. So fabrication of the components, the individual components of the UR5 robotic arm is in this particular case, assembly and integration, assembling all of the joints together, the whole overall system together, mounting it, all of these things would fall under the category of manufacturing. And also consideration of materials, consideration of which of the materials would be suitable for the robotic system. And of course, a major part of material selection would fall under the category of design, but of course, the materials are being used in the manufacturing process. And of course, calibration and verification, and quality control and testing. Moving on to electronics, one of the primary components is that of controller design, and that consists of microcontrollers, motion control, digital signal processing units, FPGAs and PLCs. So the picture that you see, the bigger picture that you see here is that of a control unit for a UR5 robot. And all of these components fall under the category of controller design, which is a vast field, but I just want to give an overall picture of controller design in this particular case. And then of course, force and torque sensors embedded inside the robotic arm, joint angle sensors, stepper motors or servo motors for each of the individual joints, IMUs, proximity sensors, visual sensors or cameras, these fall under the category of sensors, and actuators. So stepper motors and servo motors are of course actuators, and the other points mentioned here point to sensors. So sensors and actuators, another subfield, another important subfield when it comes to electronics engineering. And then of course, interfacing, because it's a complicated system, you need to have an interface to several different components. The robotic system should be interfaced to, let's say, the tablet that is controlling it. It should be able to be used from a computer. It should be able to be interfaced and used by a USB, for example, and it should have an EtherCAT interface, a Wi-Fi module. It should have a CAN bus transceiver and an Ethernet interface. So all of the different interfaces would fall under the category of communication, and how all the data from the robotic system can actually be utilized or at least visualized for a particular scenario. And this is also a very important subcategory. And then power supply. for the robotic system to work, and so power supply unit would be an important part. Components like drive amplifiers, AC to DC converters, power electronic switches and interfaces, and all of these power electronic subcomponents that you see in this picture, these would be very important, and these fall under the category of power electronics. Now moving on to software engineering, computer science overall, and software engineering as a subcategory of it. So depending on your particular use case, whether you are doing a low level control task or a high level problem or a machine learning task, you would select either Python or C++ as a programming language of your choice. You'd of course be using Ubuntu if you want to work as a robotics software engineer, ROS as a framework, Git is a fundamental software engineering tool that is used, and a lot of other software engineering frameworks, tools, and skills are required to be a successful robotic software engineer. A simulation engine like Gazebo. So all of these would fall under the category of software engineering, especially if you want to work in the robotics domain as a robotics software engineer. So I have a separate video, a more detailed video where I talk about the top skills in robotics, and there I talk about all the programming skills, there I talk about all the software engineering skills, all the meta skills, all the mathematics skills. So if you are interested in the software side of robotics, I'd highly encourage you to check out that detailed video, and hopefully that would give you a comprehensive overview of different skills that are required to work in robotics in the software domain. And then moving on to artificial intelligence, let's talk about the pick and place scenario that we chose for this particular problem. So let me go back to the first slide here. So this particular case study here, so far we have let's say built the mechanical system, we know the kinematics and dynamics of it, we have designed the gripper, we have manufactured it, for example, hypothetically speaking, and then we have two particular tables, and the task is to move an object from one table to another. And of course, for using forward and kinematics and inverse kinematics, you'd be able to find out the end effector positions and orientations, and also the joint positions and orientations if that is needed, and you'd be able to manipulate the object and move it to a particular different location. Now let us consider in this particular setting that we do not know the position of the object. And this is where the robotic system needs to be intelligent, and this is why artificial intelligence algorithms would play a role here. So what if we do not know the position of the object? If we do not know the position of the object on the table, and we assume that there is a camera mounted on the top of the table, what we'd be doing is we'd be collecting sets of data and actually training a machine learning algorithm that would be able to then identify or detect the object on the table, and from that position, or whether it be a 2D position or a 3D pose estimation approach, we'll be able to get the position and orientation of the object, and then from that information we get the grasp pose where the end effector should be moving, and that way we'd be able to define the trajectory. The robot would be able to grasp the object and then place it to a fixed position on the second table. So to do that, what we would do is we would use computer vision, deep learning, and we'd be dealing with data captured from the images. We'd be doing object detection and or pose estimation depending on the complexity of the task, and of course every artificial intelligence problem also requires dealing with data, so we'd be handling data as well. You'd need to be connecting to the robotic system from your software interface, and you would be needing to connect it via networking protocols like TCP/IP or Ethernet, and you'd need to use ROS. You'd need to use ROS nodes to have you need to use the ROS network to actually access all the different modules of the overall robotic system. Switches, routers, hubs, and also network security would fall under this category. And serialization of the data, we are familiar with the formats JSON and XML. And then, as I mentioned, for artificial intelligence problem, data science is data is of profound importance, and here data science as a separate category has been mentioned here, because data pre-processing, data wrangling and transformation, data exploration, and using separate big data processing tools like Hadoop and Spark would fall under this category. So data, of course, you could classify data science also under artificial intelligence in a way, but artificial intelligence has more to do with actually designing and developing intelligent algorithms, and the part that is dealing with data, with large amounts of data, that can be categorized then as as a separate field, which requires the use of databases, data storage and retrieval systems, and data processing tools that I mentioned. So in this particular case, to train a machine learning agent, or develop a computer vision pipeline that is able to detect the object, you need to train a specific machine learning model on the data captured from the camera. So all of this data needs to be collected, needs to be pre-processed, transformed, so that it is usable to the machine learning model and actually performs the task that we want of the robotic system. Now, coming to the question of how do you choose a subfield? We have seen that there are so many fields, and in this particular case study of pick and place application that I just talked about, I've covered a few of the subcategories, but not all of these subcategories. So there are two particular ways that you can use to actually choose a subfield for yourself. So one is to decide, let's say, 5 to 10 different subfields of your interest. So for instance, maybe you find kinematics and dynamics very interesting, you find computer vision interesting, you find reinforcement learning interesting, you find deep learning specifically interesting, and a few other fields. So what you can do is take up very small projects in each of the subcategories. So for computer vision, it can be object detection, or learning pose estimation, or a simple problem that just gives you some idea about the kind of projects that you would deal with if you were to work in computer vision. You could take up some simple mini kinematics and dynamics project, and that could be, let's say, building a simple drawing 2 degree of freedom robot arm for drawing specific shapes. A very simple project, but that would it essentially give you the idea of what to expect in kinematics and dynamics. Or designing a simple mechanism for the gripper, that could also fall under the category of mechanical design, and that is something, if you're interested in that, is something you can explore as well. So this is one particular approach, to take up one mini project in each of the categories that you're interested in, and eventually filter it down to just one or two subfields of your interest. So this is one approach. Another approach, which is slightly more complicated but would give you more exposure, it would also take you more time, but if you have the opportunity and the time to do that, I'd encourage you to try out this approach as well, is to take up one larger interdisciplinary project that requires you to develop skills in multiple areas. And this could be, let's say, building a small mobile robot, a small cleaning robot. It could be a pick and place system, very simple robotic manipulator system, not of a larger scale, but of a simple. You can take up a simple toy project. So that is something that would give you exposure to multiple different fields in robotics and AI, and this way you can then choose which area you want to focus on, or which one or two particular areas you're most interested in. So this is how you would choose a subfield. And This was just a brief overview of all the different subcategories of robotics and AI, and hopefully the case study helped you link all of the different subcategories and how they are actually implemented in a real world or a pseudo real world project. And the goal of this video is to actually then help you define some projects for yourself that would allow you to choose one specific niche for yourself. So doing multiple projects or one large project and then choosing a field, choosing one particular project, choosing one particular field where you want to establish your career in. So all of these things are something that I plan to cover in a larger course, a more comprehensive course that I've titled Become a Self-Taught Robotics, Computer Vision or Machine Learning Engineer. And if this is something that is interesting to you, you can join the waiting list that is only available till 31st of January. And when the course would be released, if you have joined the waiting list before 31st of January, you would be given a significant benefit, a significant discount on for the fact that you are an early supporter of the course. And any specific feedback or any specific module that you want me to cover in the course, I'd be happy to know that. So feel free to share or talk about that in the comments below. And if you're looking for a free system, a free roadmap that would allow you to have a structured approach to learning robotics and AI, you can watch my video on the complete roadmap to start learning robotics and AI in 2023, and that not just gives you that gives you a yearly plan that is split into monthly and weekly goals and tasks that you can start following immediately, and you can create a plan for yourself. And it covers modules like cultivating your mindset, but also how to select a project, how to find jobs, how to build a portfolio, and a lot of different practical aspects which are not talked about in typical robotics, computer vision, or machine learning courses, which are technical in nature but which do not cover most of the overall aspects that are required to work professionally in the industry.